Hello and welcome to Otten Math. In this edition of Otten Math, we're going to talk about the area of a triangle. We're going to incorporate what you've learned before in middle school about the area of a triangle as 1/2 base times height, and then the trigonometry which you've learned to calculate the area of any triangle, right or not. Then we're going to apply this knowledge to real-world application. I know it's a little out of order. And then we're going to find the area of a segment of a circle. All right, so we want to find the area of a triangle given two lengths, two sides, and then the measure of the included angle. So we say included angle is the angle which is sandwiched, that's my words, between the two sides. So in this case, the two sides would be A here in red and lowercase b, and then the included angle would be this uppercase C. So side lengths typically have a lowercase and angles typically have an uppercase. So knowing that this is a side angle side triangle, so we're given a side, included angle and a side, we can use this information to find out the area of any triangle. All right, how does this work? So we have the same triangle before, triangle ABC, and we know that the area of the triangle is 1/2 base times height. In this case, we're going to say the base here is length B, and the height here is height H. So we're going to say 1/2 H times the b, lowercase b is going to be the area of our triangle. All right, so we're going to use what we've learned in trigonometry. We know that the sine of C is equal to the side opposite C divided by the hypotenuse. So drawing the altitude here, and the length here is h, I take the sine of C and I end up with h over a. So I can rewrite then sine C is equal to h over a as h is equal to a sine C, and then substitute a sine C for h, and we end up with the area of triangle ABC, which is not a right triangle, or not necessarily a right triangle, is 1/2 BA sine C. And you can do that for any of the angles given you have the two sides in the included angle. So 1/2 AB sine C, 1/2 BC sine A, and 1/2 AC sine B will all give you the same area for a given triangle. But again, you need to know the two sides and the included angle. So these are how the formulas look. So the area of a triangle is 1/2 the product of the two side lengths and the sine of the included angle. All right, so I'm going to give you some practice problems to work on, and then we'll go into an application problem, and then we'll talk about sectors and segments. So two sides of a triangle have lengths 7 centimeters and 4 centimeters. The included angle is 73 degrees. Find the area of the triangle. I'm going to pause here while you figure that out. All right, so 1/2 AB sine C, 1/2 7 times 4 times sine of 73 ends up being 13.4 centimeters squared. All right, next question. The area of triangle PQR is 15. If P is equal to 5 and Q is equal to 10, find all possible measures of angle R. I'm going to pause here while you figure this out. Strong recommendation to draw the triangle. All right, so we've drawn the triangle PQR, side lengths lowercase r, lowercase p, and lowercase q. Now we're going to figure out that the area of the triangle is 1/2 times 5p times q times sine of r. That's equal to 15. And 1/2 5 times 10 is 1/2 of 50, or 25. 25 sine r is equal to 15, or sine r is equal to 15 over 25, or sine of r is equal to 0.6. And we can use inverse sine in order to solve for an angle measure. Inverse sine of 0.6 on your calculator is going to be 36.9. But we know that sine is positive in both the first and second quadrants. So there are two possible answers, 36.9 and 180 minus 36.9, or 143.1. So the two correct answers would be 36.9 degrees and 143.1 degrees. Using 36.9 as our reference angle, we can see how we get to 143.1. So if I use 36.9 here, I can also say the sine of 143.1 has the same value as sine of 36.9, and you can verify this in your calculator if you want, using 180 degrees and then minus the reference angle of 36.9. That's how I get to 143.1. So on a test, I'd expect you to provide me with both answers, 36.9 and 143.1, and that's what I look for from my students. All right, so now we're going to jump to number 3. We're going to apply this knowledge from number 1 to real-world applications. And I'm going to give you the problem. You're going to work this out on your own or see if you can, then come back and check the answer. All right, so one of my former students has used his pre-calculus skills to develop an app which has made him millions of dollars. He's considering buying a $2 million piece of property and wants to know the cost per square foot. He's hired you to give him an answer. All right, so we have this piece of property, this quadrilateral, right angle here, a length of 120, length of 50, and then a length here on the right-hand side of 180 feet. And we're going to use what we know about the area of any triangle to find the area of this quadrilateral. All right, so I'm going to give you a moment. Let's see if you can figure it out. All right, so what I'm going to do is I'm going to draw an altitude or a length from B to E such that it's perpendicular to DC. And then I'm going to break the bottom quadrilateral into 2 pieces. So now I have 2 triangles, BAD and DBC. So I have a length of 50 and 120. So I know the diagonal is going to be 30. It's a 5, 12, 13 triangle. And let's just write the 0 here. So BD length is going to be 130. Now I'm going to use trigonometry to find the measure of angle ADB, and because we know ADE is 110 degrees, we can subtract what we know for the value for tangent of that angle, or that angle measure based on inverse tangent, to find the measure of BDE. All right, so first we found BD as 130 feet based on our 5, 12, 13 triangle. We created a right angle here and a right triangle. And then we use a tangent, inverse tangent of 12 over 5 to find the angle measure of ADB at 67.4. So you're going to need your calculator. Inverse tangent of 12 over 5, or 120 over 50, is equal to 67.4. And then from there, we subtracted 67.4 from the given angle measure of ADE to derive the angle measure of BDE at 42.6. All right, so let's take on the measure of ABD first, so BAD or ABD. It's going to be 1/2 of 120 times 50 times, we could say sine of 90, but sine of 90 is just 1. So 1/2 base times height is 1/2 120 times 50, which ends up being 3,000. So 1/2 of 6,000 is 3,000 square feet. Now let's find the area of DBC. DBC, or this larger triangle. That's going to be 1/2 of 130, so this length side, times 180 times the sine of 42.6, which we derived by subtracting 67.4 from 110, and you end up with 7,919. All right, so moving forward, we're going to add 3,000 plus 7,919. We get 10,919 square feet. We're going to divide that into $2 million, and we end up with $183.17 per square foot, and that's the cost that we are getting for my former student. Okay, moving on. You can pause here if you want to work this out on your own. Let's talk about segments and sectors of a circle. All right, so you want to find the area of a segment of a circle. And let's first talk about what a segment is based on a sector. So before we've talked about sectors of circle. Sector is the wedge of a circle. It's an area bounded by 2 radii and the intercepted arc. It's proportional to the fraction of the total area of the circle relative to the central angle. All right, so let's find out the sector based on some information. I have a radius of 6 and a central angle of 80 degrees. What's the area of the sector? So we're going to reference that 80 degrees and the radius of 6 to find out the area of the sector. So we know that the area of the circle is pi r squared. Pi r squared is going to be 36 pi. And we know the fraction that's represented by the sector is based on the central angle to the total number of degrees in a circle. So 80 divided by 360 times the total area of the circle, 36 pi, leaves us with 8 pi units squared. So the area of the sector, 8 pi units squared. Now the segment of a circle is just this area here that's defined by a chord. And it would be just basically that if I were to draw a chord from A to C, it would just be this area here that's a portion of the sector. All right, so we're going to say the segment is a portion of the sector, and we can figure out the segment by subtracting a triangle area from the sector area. So let's go ahead and do that. We'll find the area of a segment of a circle whose radius is 6, back to that same sector, but now we're calculating the segment whose central angle is 80 degrees. We're going to use 3.14 for pi, and we're going to round to the nearest tenth. Let's see if you can figure this out. I'm going to come back and go through the answer. All right, so the segment is equal to the sector, which we found to be 8 pi, minus the area of the triangle. We know that the side lengths of the triangle are 6 and 6 because of the 2 radii, and we know that 80 degrees is the central angle. And based on what we learned before about areas of the triangle, we can say the area is 1/2 the 2 side lengths times the sine of the included angle. 1/2, 6 times 6, 36, 18 times sine of 180, you should get approximately 17.7. So the segment of the circle we defined as 7.4 units squared from the prior discussion is equal to, the sector we found out is 8 pi minus the area of the triangle, 17.7, using 3.14 for pi. We end up with a segment being 7.4 units squared. Right, so if we recall, we go back to our sector value, 8 pi units squared, a definition of a segment, figuring out the area of a triangle using what we know about the formula for the area of the triangle, 1/2 side length times side length times the sine of the included angle leaves us with 17.7. Subtracting that from 8 pi leaves us with 7.4 units squared, and that's the area of the segment. All right, that's it for this edition of Otten Math 9.2 and finding the area of a triangle using 1/2 base times height and what we know about trigonometry and its relationships of side lengths and angle measures to define 1/2 AB sine C, 1/2 BC sine A, and 1/2 AC sine B as the formulas, alternative formulas for the area of any triangle. Join us next time in the next edition of Otten Math when we talk about the law of sines and cosines.